this video we're going to take a look at controlling a stepper motor, the Pic16F676 chip, by pressing a button. The 28BYJ-48 stepper motor is a 5-volt unipolar stepper motor. They draw a high current, so you can see I've used a power supply unit to the right of the breadboard. This is highly recommended. Do not try and run this from your Pic16F676. The unit on the left is a UNL2003 driver board. The stepper motor and the driver board can be purchased quite cheaply on eBay or any other shopping outlet. Here you can see the schematic diagram for the stepper motor. Here we've got a push button connected to pin 4. So here on pin 10 of the Pic, we put a jumper wire between pin 10 and pin 1 on the UNL2003 motor board. Then we have another jumper wire going from pin 9 to pin 2 on the board. A third one going from pin 8 to pin 3 on the ULN board. And the last jumper wire going from pin 7 of the Pic to pin 4 on the UNL2003. Here you'll notice we've got a separate 5-volt power supply to drive the stepper motor. So in the early videos I showed you how to create the new project. So in the description you can see pin 1 of the driver board goes to RC0 and pin 4 goes to RC3. In this sketch I have set a couple of the pragmas slightly different to the past. Obviously we're going to use the internal oscillator. The watchdog timer is off. The power up timer is enabled. The master control clear is off. And the brownout detection is enabled. The other two protection bits are off. I include the XCH library and define the X crystal frequency of 4 MHz. I then define an SW, which is for the push button, as RA3, which is pin 4. We then go into the void main void and we set up the Ansel, Tris-C, port A and port C as 0x00 as we have done in the past. I then set another variable called sign char step equals 0. This is used to store the switch case state at 0 at startup. We then have the while loop. The next line of code is this one here, which is switch brackets step. Now this is used to create each of the stages to get the stepper motor to rotate. So here you can see we've got case 0, port C equals 1. Now this means the 4 pins that we've allocated, 3 of the ports are turned off, but bit 1 is turned on, so RC0 is high. The brake is used to come out of that case. To get the stepper motor to do 1 revolution, we need 8 stages, and here are the 8 stages, and you can see different bits are being set as we go along. The thing to remember is this stepper motor is geared to 1 revolution of the drive shaft. Actually, the output shaft is on a gear ratio of 1 in 64. So it takes 2038 steps to do a full revolution. Here you can see the if statement, which is if RA3 equals 1. We then have a delay, which is a single underscore delay, and in the brackets is 2. This represents 2 clock cycles and not 2 milliseconds. This is used for debouncing. We then have another if statement, if RA3 equals 1, step plus plus. So basically when we started, the case was set to 0. So if the button has not been pressed, we then move into case 1. You'll then notice the else step minus minus. If the button has been pressed, that will decrease the step case. So if we were already on 1 and the button had been pressed, it would then move to 0. You can now see we've got two other if statements. The first one here, which is if step is greater than 7, step equals 0. So that resets it back. So if it's reached 7, for it to carry on rotating, it needs to go back to 0. The second if is if step is less than 0, step equals 7. So when it reaches 0, it needs to go back to 7 to carry on rotating in that direction. Then we have underscore delay underscore milliseconds set as 1. This is used for the speed of the stepper motor. So 1 is the fastest it can go. If you wish to slow the stepper motor down, increase this up to whatever speed you want. You'll reach a certain point where it will not rotate, and I'm not sure what that figure will be. The code will be made available on my GitHub page in the next day or so.